Hi, welcome back to Moose in Chemistry. Today we're going to talk about stoichiometry. Some people like that, and some people like, oh no, not stoichiometry. But stoichiometry is actually pretty cool, and it's actually very, very important in chemistry. There are actually two types of stoichiometries that we're going to be looking at over the next series of lessons in this area. One type of stoichiometry is called composition stoichiometry, and that's the mass relationships of elements in a compound. So in essence, how much say, for example, sodium chloride. If we're talking about sodium chloride, what is the mass of sodium in the sodium chloride? Or we might want to find what is the mass of the chlorine and its relationship to the total mass of the entire compound. So basically, when we talk about composition stoichiometry, that's what we're kind of dealing with. And again, we're going to see a lot more examples of these in further videos. Today we're going to focus, however, on reaction stoichiometry. Now, reaction stoichiometry is a little bit different. It's the mass relationship between reactants and products. Now, in an earlier lesson, we talked about reactants and products when we were talking about balancing chemical equations. Remember that when we balance chemical equations, we have reactants plus reactants yield products plus products. So what we're going to do in reaction stoichiometry, we're going to figure out the mass relationship between one particular reactant and a product, or another reactant and another product. There's a whole bunch of ways we can look at this, but the best way to do this is just do it. So let's go ahead and erase this out of our way. Okay, let's go ahead, like I said earlier before let's go ahead and erase this real quickly, and let's put it together. So we're going to erase all this, and we're going to get this taken care of real fast here. Again, I wish I had a bigger eraser, but maybe Lenzo will do that sometime in the near future. Although it's a really pretty good program. I really enjoy using it so far. All right, so now let's take an example of this particular problem. Okay, here's the first problem we're going to look at. The elements lithium and oxygen react very violently to form lithium oxide, which is Li2O. How many moles of lithium oxide will form if 2 moles of lithium are used in the reaction? The first thing we have to do is, it's kind of like a word equation that we talked about in an earlier video. So what we need to do is we need to write down the skeleton equation. So we have lithium plus oxygen. Remember that oxygen's O2 because it's diatomic. All right. So anyway, that yields to form lithium oxide. So now, how do we know that this is correct? Well, remember that oxygen carries a -2 charge because it's in group 16 and it's in the anion position. And lithium has a +1 charge because it's the cation and it comes from group 1. So let's go ahead and make this work. So first of all, I want to erase some of this here. So what I've taught my students is if you have 2 different oxidation numbers, simply crisscross. Crisscross means switching them. So erase that real quickly. And that means I'm going to put a 2 here. So that gives me lithium oxide. That's the correct way. Now what I want to do is I'm going to want to put a 2 in front of the lithium oxide because I only have 1 oxygen and right here I have 2. So I need at least 2 oxygens. So when I do that, that means I'm going to need to put a 4 right here to balance out my lithium. Now, the next thing I need to do is figure out what are my mole ratios. And in an earlier video, we talked about mole ratios. So let's go ahead and write all the mole ratios. So when we're writing the relationships, these mole relationships, we're going to have 4 moles of lithium over 1 mole of oxygen, 4 moles of lithium over 2 moles of lithium oxide, 1 mole of oxygen over 4 moles of lithium, and 1 mole of oxygen over 2 moles of lithium oxide, and finally 2 moles of lithium oxide over 1 mole of oxygen, and 2 moles of lithium over 4 moles of lithium. Okay, now that we've decided what our mole ratios are, let's look at the problem. It says how many moles of lithium oxide will form if 2 moles of lithium are used. So we have 2 moles of lithium, and so we're going to go 2 moles of Li times our mole relationship. Now, we want to convert moles of lithium into moles of lithium oxide. So we're going to want the relationship that has moles of lithium on the bottom and moles of lithium oxide on the top. So we're going to look for this relationship right here. So what we're going to do is we're going to put down 4 moles of lithium on the bottom and 2 moles of lithium oxide. Okay, so now moles cancel out, and this gives me 4 moles of lithium oxide over 4 moles of lithium. So this gives me, and of course our lithium gets canceled out. So let's go ahead and erase this. So this gives me 4 over 4 basically. So let's just put 4 over 4 here because our LI's got canceled out. And that's going to equal a total of 1 mole of lithium oxide. Okay, let's go ahead and clear this problem, and let's try another one. Okay, in this problem, we have how many moles of ammonia are produced when 7 moles of hydrogen gas react with an excess of nitrogen gas. Okay, so first of all, we need to write the equation. Nitrogen, oh, that's right, nitrogen is diatomic. It's one of the 7 diatomics. Remember those? And then we have hydrogen. Oh, that's another one of those 7 diatomics, because it was hydrogen, nitrogen, oxygen, chlorine, fluorine, and then also don't forget bromine and iodine. This is 1, 2, 3, 4, 5, 6, 7. They're the 7 diatomics. All right, let's go ahead and erase those anyway. Just kind of remind you about the diatomics. When these elements are in an equation or in nature, they usually occur with themselves and are rarely ever solo. Kind of like a Billy Idol, like I'm dancing with myself kind of type element. So anyway, I know not a good job of Billy Idol, but I don't even know you guys know who he is. But anyway, so this gives me NH3. Now, oh look, we have 2 nitrogens here. So that means we're going to have to put a 2 in front of there. And when I do that, that gives me 2 nitrogens, but that gives me 6 hydrogens. So I need to put a 3 here. Now, we could go and write all the molar relationships like we did the last time. But, we really don't have to do that every time. Notice that we have 7 moles of hydrogen gas. And it's going to react with ammonia. It's going to make ammonia. So how many moles of ammonia? So looking for moles of ammonia are produced when 7 moles of hydrogen gas react with an excess of nitrogen gas. Oh, okay. So we've balanced the equation. So we're going to start off with 7 moles, that's what we know, of hydrogen gas. And we want to know how many moles of ammonia. That's this stuff right here. That's ammonia. How many moles of ammonia are produced? So we're going to multiply that by 2 moles of ammonia. And our hydrogens have 3 moles because this is the molar relationship. There are 2 moles to every 3 moles in this reaction. So there's 2 moles of ammonia to every 3 moles of hydrogen. That's what that means. All right. So now we're going to go ahead and multiply this. This is going to give me, and the hydrogens cancel out, this is going to give me 14 over 3 moles of NH3, which is equal to roughly 4.67 moles of NH3. And that's our lesson for introducing reaction stoichiometry today. And I hope you have an awesome day, and we look forward to seeing you back at Moose in Chemistry.